All right. So last time we went through 18.1. If you missed it, the recording is up. And I'm going to go down here. Okay, so 18.2 is all about these calculations involving acids and bases, specifically weak acids and bases. Okay, if you have a strong acid or base, you don't have to do all of this. Strong acid and bases are a lot easier because since they fully 100% ionize or dissociate, you can assume the calculation of the concentration of the acid and the concentration of the hydrogen ions for an acid or the hydroxide ion for a base. You can assume that they're equal because everything should split and dissociate 100%. Okay. For weak acids and bases, since the definition of them is that they don't fully dissociate or they don't fully ionize, we have to do these extra steps in the calculations. And so it's not as easy as just doing the pH equals the negative log of this. We're still going to do that, but we have to do some other calculations before we can calculate things like pH directly. So we're going to get introduced to these things. It's called the dissociation constant, and so it's like an equilibrium constant because in equilibrium we had like Kc, where we said that's just the equilibrium constant, and then sometimes if it was gases it was called Kp for pressure. Well, it's that same concept right now, except we're going to have Ka and Kb, and the A is for acid, the B is for base. So Ka is going to be the dissociation constant for a weak acid. Kb would be for a weak base, okay? And if you have a conjugate acid-base pair, okay, going back to that Bronsted-Lowry definition, if you multiply their values for Ka and Kb, you get what we call Kw, which is the ionization constant for water. And we know that number, Kw, is always equal to the same number as long as you're at a temperature of 298 Kelvin, which most of the time we are for problems. You'll see that it's going to again relate similar to like how pH was the negative log of the hydrogen ion. Well, we have this thing called pKa. Okay, so instead of pH, it's pKa. And it's the negative log of that acid dissociation constant. And then the same thing for the base. pKb is going to be the negative log of the dissociation constant for the base. So you're doing the same equations for acids and bases. It's just sometimes for bases, there's extra steps. Because if you're given the concentration for a base, you have to keep in mind that's going to relate to hydroxide ion concentration. And so once you calculate the hydroxide ion concentration, you then have to calculate hydrogen ion before you can do pH. So sometimes bases have a little extra steps in them than the acids do. Okay. So we're going to look today at problems that are going to involve hydrogen ion concentration, hydroxide ion concentration, pH, pOH, and then the acid dissociation constant and pKa, the base dissociation constant and pKb. And we're going to kind of see how it like all comes together and how you would work out different types of problems. And then you should, based on the values for like Ka, pKa, or Kb, pKb, if you're given values for those, you should be able to kind of rank or talk about like which acids or bases are stronger or weaker in comparison to each other. One thing I mentioned, the Kw value, it is temperature dependent, and there's a section we're going to talk about that. I think it's the last section in today. But you can pretty much assume anytime you're doing problems like this, you're going to be at that temperature, unless they tell you differently. But that usually doesn't happen. I don't think I've ever seen it happen. The calculation so buffer solutions, we're actually going to get to that next time in 18.3. And so like it says here, it's only going to be assessed in these options. So, and we actually don't have to cover options this year. They took that out of the test. That was paper 3 that they took off. And then it says you're only going to have to involve doing 1 proton being transferred. You're not going to have to do anything that would give away 2 protons. You can do something at other temperatures, but like I said, it doesn't happen that often. I've rarely seen it happen. And then you should talk about when we use approximations, because as when we get down to the ice boxes later, we're going to make some assumptions and some approximations on some of the numbers, and we're going to talk about that. This one's a really big one. They're not going to, and there are some weak acid-base calculations when you do the ice boxes that because of the way the numbers work out, you have to use like the quadratic formula in order to calculate, everybody's favorite math equation. But for IB, you're not required to do that. So you're not going to have like really super complicated calculations like that. Okay. All right. So I'm going to scroll down here to 18.2 to start. Okay. So the basic introduction goes over, just sort of recaps weak acids and weak bases. So the term weak, it just means that they partially dissociate or ionize. Ionize and dissociate are synonyms. They mean the same thing. So you'll see one or the other used in questions. And so all weak acids and bases, their reactions, they're actually equilibrium reactions. If you notice, they get the double arrow because they're equilibrium reactions, and the equilibrium, what's favored is the reactant. So the equilibrium is going to be over here on the left because more of your acid and base is going to stay together. It's not going to break apart and form the conjugate very easily because they're weak. Strong acids and bases, it all fully dissociates, and there's just a regular arrow, no double arrow. Okay. But since these are equilibrium, that's why all these concepts of like that relate to like the equilibrium constant and ice boxes are going to apply to weak acids and bases and their calculations. Okay. So this first equation is, this is acetic or ethanoic acid. And when you dissolve it or react it in water, what happens is the acid is going to donate this hydrogen, this proton. So you end up with hydronium, and you end up with the acetate or the ethanoate ion. Base, same thing. Here's my ammonia. So it's going to accept a hydrogen from the water and then form the ammonium ion. And then you'll have hydroxide ions floating around in there too. Okay. So what's going to happen though is you're not going to have very many of these ions on the product side, very, very few, because it's a weak acid and base. Okay. So when we talk about Ka, which is the acid dissociation constant, it's just the specific equilibrium constant for the dissociation of a weak acid or the ionization of a weak acid. Okay. And Kb is the same thing, but for a weak base. All right. A lot of times we don't include water in the expression. So you know how when we would write Kc expressions, we'd be like Kc equals, and it'd be the concentration of whatever products we had, and they'd be multiplied. And then it would be over the concentration of the reactants. Okay. Same concept. We're still setting up those equations. The one thing that's going to be easy is usually you're not going to have any coefficients in these equations because just the nature of how the formulas for the acids and water and bases are written, usually everything is a 1-to-1 ratio. So usually you're not going to have any exponents in your equation. And then we eliminate water because it's more or less constant. And so since it's usually constant, we kind of eliminate it. And so if you notice, H3O plus is the same thing as H plus. Okay. I could rewrite this equation. I could just put like the acid, and I could say it's going to dissociate into hydrogen and the negative anion. Okay. And so these two equations are showing the same thing. It's just this one, I'm including the water. So it's hydronium so that it's balanced. In this one, I eliminated the water because the water is not really doing much. It's a constant. It's just kind of there helping the acid to dissolve and dissociate. And so we write the Ka equation based on this one. We leave the water out. And so if you notice, the products are the hydrogen ion concentration and the concentration of our anion, our negative ion, on top, multiplied. And then the bottom is the concentration of the weak acid. Okay. So that's always the setup to find Ka. So if you know all three of those concentrations, you can plug them in and solve for Ka. If you know Ka and two of the concentrations, you can plug that in and rearrange the equation and solve for your missing concentration. And so those are some of the calculations you're going to do. Sometimes you'll calculate Ka. Sometimes you might be asked to calculate the pH. And if you're calculating the pH, basically you're going to have to solve for this hydrogen ion concentration here and then do the negative log of that value to get the pH. Okay. Base dissociation constant, same basic premise. The only difference is you got like B's instead of A's, and you got hydroxide instead of hydrogen ion concentration. Okay. But the same basic concept in that we're leaving the water out. And so we just have the conjugate acid is up here, and then the hydroxide ion concentration, and then we have our weak base on the bottom. Okay. But same setup. And then on this one, what will be a little extended, I guess you could say, or a little different on the calculation here. If you're asked to calculate the pH of a weak base, you will use this equation to calculate the hydroxide ion concentration, And then once you have that, there's two ways you can go about it. You can use, the fact that we know that the hydrogen times the hydroxide equals water ionization constant. And you can plug in the hydroxide constant and the Kw and solve for hydrogen ion and then do negative log of the H plus. Or you can do negative log of that hydroxide ion, and that'll give you POH. And then you know that pH plus POH equals 14. So you can just subtract it from 14. So there's a couple different ways you can do it, but you always start by solving for the hydroxide ion concentration and then using one of these two methods. Okay. So your first sort of practice exercises are just practicing writing what would the Ka and Kb expressions be for these. So that's pretty straightforward. You're just going to do exactly what we just kind of looked at on those examples. The only thing is to remember that you are leaving out the water. So instead of hydronium here, it'll just be H plus, okay? All right, so how do these kind of relate to each other? We saw this at the beginning. pKa, similar to pH, it's a logarithmic calculation. So, you can see it's set up similar. Instead of pH is negative log of H, we have pKa is negative log of Ka, okay? And then pKb is related the same way. And then just like, when we would solve for like the hydrogen ion concentration, it would be 10 raised to the negative pH. Same thing here, 10 raised to the negative pKa is going to give us Ka, and then same thing for pKb and Kb. So the relationship is the same. It's just this is for those weak acids and bases because we can't use the hydrogen ion concentration since they don't fully dissociate. Okay. pKa and pKb they're usually positives. They don't have units, just like pH does not have units. And just like the pH scale, if you change your pKa or pKb by 1 unit, it's a 10-fold change in the value of your constant. So just like pH, if we went from like a pH of 3 and we went down to a pH of 2, that was a difference of 1, but that means that we increased the hydrogen ion concentration times 10, okay? So same type of relationship here with pKa and pKb and Ka/Kb, okay? And then they do have to be quoted at a specific temperature. Usually they'll tell you in the problem, so you'll know if you have to do anything differently. So here's how you kind of relate it to the relative strength. They have an inverse relationship. So the stronger the acid, the higher the value of the Ka and the lower the value of pKa. And then same thing for strong base or strong weak bases, okay? So if you have something that has like a high Ka and a low pKa, that's going to be a stronger acid than something with a lower Ka and a higher pKa. So they're inverse related. And then base, you can see it's the same thing. If you have a high Kb and a low pKb, that would be more a stronger base compared to something that would have a lower Kb and a higher pKb. So if you're given values, which is what you're doing on this exercise, it's giving us, there's 2 acids and 2 bases, and they want you to identify which is the strongest acid and strongest base from the table based on the pKa values they give you. And so again, you just kind of have to remember the concept up here of how things are related. All right, so now we're going to get into calculations, okay? So this one, we have Ka, Kb, and Kw. So it says for a conjugate acid-base pair, we talked about that when you multiply them, they're going to equal Kw, okay? And Kw, remember, as long as we're at 290 Kelvin, which we usually are, Kw always equals 1 times 10 to the negative 14, okay? So what ends up happening is if they give you if they give you Ka and they want you to solve for Kb, you can use this equation. If they give you Kb and they want Ka, you can use this. You just plug them in and rearrange it to solve for the missing one. So they've given us this reaction. We can see the weak acid is ethanoic acid. And so they tell us that the Ka of this weak acid, here's the Ka value. And we should know this is something that doesn't change. Kw is always 1 times 10 to the 14 as long as we're at that temperature. So I'm just going to plug it in. And so since I'm solving for Kb, I can rearrange the equation. Kb is Kw divided by Ka. And that's what they've done here. Here's KW value on top. Here's the KA value on the bottom. You divide them in your calculator and you get this answer. Notice they kept the sig figs the same. So both of these had 3. So my answer has 3 sig figs. Okay. And then similar to how with like pH and pOH, they added up to equal 14. As long as you're at that temperature, pKa and pKb should equal 14 as well. Okay. So again, you can take out the Ka and Kb and substitute like hydrogen and hydroxide ion, and you would be getting, you know, the relationships and the equations are exactly the same. Okay. And so keep that in mind. If you're solving for pKa and they give you pKb, just subtract it from 14. Okay. So how this applies to calculating, doing some calculations. So there's a couple different things. Now on the pre-recorded stuff, there were 2 videos. The first one went through how to calculate Ka when you're given concentration. The other one went through what we're going to look at right here, which is actually calculating the pH. So there's sort of 2 different things you might be asked to calculate. So definitely, if you haven't watched the other videos, make sure you go watch them. But one of them, if they ask you to calculate Ka, which is what's not on here, usually they're going to give you the concentration and you can calculate you doing that. Now, if they ask you to calculate pH, this is what you're going to do is set up an ice box. Okay. So this one, they tell us that here's the concentration and it's a solution of ethanoic acid. Ethanoic is a weak acid. That anytime it's a weak, that means I need an ice box. Okay. So notice that we have plugged in 0.750 for the initial concentration of the ethanoic acid. Okay. And if you think about this, we're talking about the acid dissociating. So you have to kind of remember that it's the acid. And then my products are going to be the conjugate base after it's lost a proton. And it's going to be that proton that it lost. Okay. Because we're eliminating water. So we're not going to put water on the reactant side and hydronium on the product side. So when you're doing these equations, you're only going to have one reactant because it's going to be the acid or the base. And then your products are going to be whatever the conjugate is, and then the hydrogen ion or hydroxide ion for a base. So we plug in the initial concentration of the reactant of the acid. Now, at the start, these are both products. So we know that they don't have a concentration at the beginning because there are no products, okay? Unless they tell us we're starting with some. Okay, which usually you won't. Everything in these is always a 1-to-1 ratio. And so on this one, notice we have negative X here, but we're adding X here because the products are going to go up, the reactant will go down. Okay, products can't go down because they're already 0. So then at equilibrium, the concentration for our weak acid is going to be 0.750 minus X. And then for both products, for the conjugate and for the hydrogen ion concentration, it's just going to be X. And so we have to sort of figure out what X is, okay? All the problems that we are going to be given, okay, are going to be easy to do because we're actually going to simplify this. So let me clean this off a little bit so we can look at this one. Okay, so the other piece of information they gave me the Ka, okay? I know that Ka, that's the acid dissociation constant, and I know that Ka equals, for this equation, it's the concentration of that acetate or ethanoate ion. So I know that this is how I should write the Ka expression because we just looked at that up in the first part. And so then I'm plugging in values. So Ka plugs in here. I plug in all of the X's here. They go into the equation. And so if I rewrite it, I'm going to kind of write it down here where we can see it. I get, what was it? 1.8 times 10 to the negative 5th equals. And then my, the top, if you look at the top, they're both X's. So everybody can agree the top is going to be X squared because I have X for both products and they're being multiplied. So the top is X squared. The bottom is 0.750 minus X. Now, if depending on the problem, you might have to use a quadratic formula. However, there's sort of a caveat or a catch, I guess. If your Ka value is very small, meaning like something to the negative third power or smaller, which this is because it's the negative fifth, we can assume that this 0.750 minus x, we can assume that that change is not going to be very much because this is a weak acid. And so by making that assumption, what we do is we take away this minus x, and that makes the math a whole lot easier. If we leave the negative x there, then we end up having to use the quadratic formula, and there's all kinds of other weird stuff that makes it more difficult. But because we can assume that it's going to be almost exactly 0.750 still at equilibrium because it's a weak acid, and that Ka value is so small, we can make that assumption, we can simplify the math, and now it's just getting x by itself on one side. And so multiply both sides by 0.750 and then take the square root of both sides, and that gives you your value for x. And once you get x, we know from this table up here, x is the hydrogen ion concentration. So once you get x, which is the hydrogen ion concentration, then you can do the negative log of whatever you got for x, and that will give you the pH. Okay. The only difference on the second example's got a weak base. The process is essentially the same. The only difference is going to be because you have a Kb value, you're going to be solving for the hydroxide ion value. So when you get x, x is the hydroxide ion value. So if you do the negative log of x on this example 2, that's going to give you POH. There's one extra step. After you do that, then you have to do 14 minus that POH to get to pH. So if you have weak acids, you just solve for x, plug a negative log of x, and that's your pH. If you have weak bases, once you do the negative log, that's POH because it's a hydroxide ion concentration since it's a weak base, and you have to do this extra step of subtracting from 14 to actually get the pH. Okay. So in your practice down here, it's going to have you walk through. So it's like, write the equation for the ionization, and then what would the acid dissociate, the Ka expression be? Then it asks you to calculate the Ka value. It gives you the pKa. So you have equations that can help you to do that. And then it wants you to calculate some of the concentrations and the pH. Okay. So keep in mind that you're doing exactly what I just kind of talked about on the examples. Obviously, the numbers are going to be different, but the process is going to be the same. And so number 1 is an acid. Number 2 is a weak base. Okay. The last little part here that I think is just talking about the temperature dependence. So it's just reminding us that for Kw to actually be 1 times 10 to the negative 14, it has to be at 298 Kelvin. Okay. And that's because the dissociation of water, it requires energy. So that means the forward reaction's endothermic, the reverse reaction's exothermic. And so it is dependent on temperature, and temperature will affect it because temperature will cause the equilibrium to shift in one direction or the other, like Le Chatelier's principle says. And so when you guys go and you're watching the video, they actually go through this because at 298, the hydrogen ions and the pH will be exactly 7 because it's equal, right? Or it's neutral, I mean, in the middle. But if you shift it up and this number changes, the hydrogen ion concentration are going to be a little higher or lower. So the pH is not going to be exactly 7, okay? But as I said, most of our problems are going to be at that temperature. There are not going to be very many, if any, that will not be at that temperature. All right.